Welcome back to the deep dive. I have to say, usually when I pick up the source material for what we do here, I feel like I'm adding a layer of paint to a wall I already know exists. I'm learning new details, sure.
Filling in the gaps.
But today feels different. Today feels like we're taking a sledgehammer to the wall itself.
That is a very, very appropriate metaphor.
I mean, I'm reading through this analysis of the history of space and time, which, by the way, is incredibly dense stuff, and I'm realizing that the ground I'm standing on, the clock on my wall, the very feeling of now that I'm experiencing,
It's all an illusion.
it's all a lie. Or at least it's a very convincing illusion.
A very persistent one, as Einstein might say.
And that's what we're tackling today. We're looking at the fundamental nature of reality. We're taking this historical and scientific analysis, which traces the evolution of cosmology from the Greeks all the way to the modern day, and we're going to try and understand why our common sense is basically the worst tool we have for understanding the universe.
It really is. Common sense is, it's great for surviving on the savannah. It's fantastic for not walking into traffic.
Right.
But when you try to apply that same common sense to the cosmos, it fails spectacularly.
So here's my confession to start us off. I consider myself a logical person.
Yep.
You know, I trust my eyes. If I drop my keys, they fall down. If I look at my watch, a second is a second, whether I'm sitting here or flying in a plane. That feels like an absolute truth.
And that is exactly where we need to start. Because that feeling, that deep intuition that space is a fixed stage and time is a steady, universal drumbeat, that is the common sense view that humanity held for thousands of years.
And the story of physics is the story of how we realized that was wrong.
Slowly and very painfully, yes.
Painfully is right. My brain hurts just thinking about the outline we have to get through. We're going to talk about why gravity isn't really a force, why time is personal, and why a clock on top of a water tower actually runs faster than one on the ground.
It sounds like magic, but it's measurable. It's how the universe actually works. And it's kind of beautiful when you get your head around it.
Okay, so let's go back to the beginning, or at least the beginning of Western scientific thought. We have to talk about Aristotle.
The great classifier, the man who set the rules.
Now, in the source material, Aristotle is presented as the guy who, laid down the law for nearly 2,000 years. And I have to be the devil's advocate here for a second. Aristotle's physics makes total sense to me.
Of course it does. It describes your everyday experience perfectly.
Exactly. Aristotle said the natural state of a body is to be at rest. If I slide my coffee cup across this table, it moves for a bit, and then it stops. It wants to stop. If I don't keep pushing it, it quits moving.
Exactly. And because we live in a world that is completely dominated by friction, that is what we always see. To Aristotle, motion was something unnatural. It required a motor or a force to maintain it. The moment the force stops, the motion should stop.
He also had this idea about falling objects that, again, feels really intuitive.
Yeah.
The heavy body fallacy.
Yes. Aristotle was convinced that a heavy object falls faster than a light object.
Which, again, feels true. If I drop a rock and a feather, the rock hits the ground first, every time. The feather just kind of floats around.
And this is where the problem starts. Aristotle didn't distinguish between the fundamental laws of motion and the environmental factors that get in the way, like air resistance. He saw the rock fall faster, and he formulated a universal law. Heavier bodies fall faster in proportion to their weight.
But the source makes a really interesting point about the methodology here.
Wow.
It's not just that Aristotle was wrong, it's how he was wrong that mattered so much.
Right. The entire Aristotelian tradition was built on pure thought. They believed you could deduce the laws of the universe just by thinking clearly about them. They didn't feel this burning need to, go out and actually measure things.
Like, why bother?
To them, it logically followed that if the Earth pulls on a heavy stone more than a light one, which it does, then the heavy one must rush toward the Earth faster. It was self-evident.
It's almost like they thought checking the math was beneath them. Like, why would I measure it? It's obvious.
Exactly. And that obviousness held back physics for almost 20 centuries until we get to Galileo Galilei.
The man who dared to look. Now, everyone knows the story of the Leaning Tower of Pisa. Galileo climbs to the top, drops a cannonball and a musket ball, and they hit the ground at the exact same time, proving Aristotle wrong while the crowd gasps below.
It's a fantastic scene. It's cinematic. And according to our sources, it is almost certainly a myth.
I hate that. I really want that story to be true.
I know, we all do. But the reality is actually much more impressive, much more clever. See, dropping things off a tower is messy. It happens way too fast. In the early 1600s, there were no stopwatches. You're measuring time with your pulse or a water clock.
A water clock, you mean literally weighing how much water droops out of a bucket?
That's exactly what it was. So you can't possibly measure the split-second differences of a falling rock with that kind of tool.
Okay, so what did he do?
He did something brilliant. He realized that falling vertically is just a specific, very fast version of rolling down a hill. If you roll a ball down a smooth, gentle slope, it's still being pulled by gravity, but the motion is. It's diluted, it's slowed down.
So he slows down time effectively
Yeah.
by changing the geometry.
He slows down the event so he can observe it, and he rolls balls of different weights down these long, smooth slopes. And what he finds just completely destroys Aristotle's physics.
He finds that the weight doesn't matter at all.
Zero difference. Once he minimized friction, and he was very careful, using polished bronze balls and a smooth wooden groove, the heavy ball and the light ball accelerate at the exact same rate.
This is the birth of the scientific method, isn't it? Really?
Yeah.
Choosing observation over intuition.
It absolutely is. He also realized that the feather only falls slowly because of the air. He predicted that in a vacuum, a feather and a lead weight would fall together.
And we actually proved that. I love this detail from the notes commander David Scott on the moon.
Apollo 15, a fantastic moment.
He's standing there on the surface of the moon, which is a near-perfect vacuum, and he holds out a geological hammer and a falcon feather. And the video is grainy, but you can see it. They hit the lunar dust at the exact same instant.
It's incredible. Galileo reaches out from the 17th century and high-fives an astronaut. It's a beautiful moment. But Galileo's ramps proved something else, something even more fundamental than just things fall together.
It changed our whole understanding of force.
Exactly. Remember, Aristotle thought force was needed to keep things moving, but Galileo watched his balls rolling and realized, no, if I make this ramp smoother and smoother, the ball rolls further and further. If I can make it perfectly smooth and perfectly flat with no friction,
So it'd never stop.
it would never stop. So the natural state of an object isn't rest. It's just whatever it was doing before.
Right. The natural state is to keep doing what you're doing. If you're moving, you keep moving in a straight line. If you're still, you stay still. Force isn't needed to maintain motion.
Force is only needed to change motion.
That is a massive shift. That is the definition of acceleration.
And that paves the way directly for Isaac Newton.
Okay, so Newton enters the chat in 1687 with the Principia Mathematica, and he takes these brilliant observations from Galileo and forges them into rigid, universal mathematical laws.
The foundational text of modern physics, it's impossible to overstate its importance.
Let's break down the big ones. First law, inertia. This is what we just talked about. Things keep moving unless you mess with them. An object in motion stays in motion.
Correct. The default state of the universe is coasting.
Second law. This is the equation everyone memorizes in high school but maybe doesn't really understand on a gut level. Force equals mass times acceleration.
This is the engine of classical mechanics. It tells you exactly how much an object's motion will change when you push on it. It's the predictive heart of his whole system.
The source uses a car analogy here, but I want to dig a bit deeper into it because I think this is where the why do heavy things fall the same speed question gets answered mathematically, not just observationally.
It is. It falls right out of the equation. Let's look at it. We can rearrange it to solve for acceleration, right? So all agree depends on two things. How hard you push, the force, and how heavy the object is, the mass.
Okay, so let's apply this to gravity. Let's take two rocks.
Let's say a 1 kilogram rock and a 10 kilogram rock.
So the 10-kilogram rock is 10 times as heavy.
Heavy just means gravity is pulling on it harder. So the force of gravity on the 10 kilogram rock is 10 times the force on the 1 kilogram rock.
So if the force is 10 times bigger, shouldn't it accelerate 10 times as fast? That's what Aristotle thought.
That's the trap. Aristotle looked at the pull, but he ignored the null or the mass. The 10 kilogram rock has 10 times the force pulling it down, yes, but it also has 10 times the mass.
And mass is resistance. It's inertia.
Exactly. Mass is simply a measure of how stubborn an object is, how hard it is to get it moving or change its direction. It's harder to push a truck than a bicycle. So for the heavy rock, you have 10 times the engine power, which is gravity.
But you're trying to move a body that is 10 times as stubborn.
Precisely. The 10 times the pull is perfectly canceled out by the 10 times the resistance. The ratio, via Banauer, stays the same. The acceleration is identical.
The universe balances its books perfectly.
It is deeply satisfying, isn't it? It removes the mystery. It's just math.
It is. And Newton's laws worked. They were incredible. They predicted the motions of the planets, the moons, the tides. It really seemed like Newton had solved the entire universe. But
There's always a but.
there was a ghost in the machine, a philosophical problem that really, really bothered Newton.
The problem of absolute rest.
Right. Aristotle believed the Earth was at rest. It was the fixed center of the universe. So you could always say where something was, it's 5 miles north of the center, an absolute cosmic address.
But Newton's laws completely messed that up.
How so?
Well, Newton's first law says a body stays in constant motion unless acted upon. This implies that constant steady motion and being at rest are physically indistinguishable.
We have to use the tram analogy here. This is in the source text, and I think it's the best way to visualize this problem.
Let's do it. So imagine you are on a tram or a very smooth train moving along a perfectly straight track at a steady 30 miles per hour. Critically, the windows are blacked out. You can't see outside.
Okay, I'm in the mystery tram.
You decide to set up a ping pong table in the aisle. You start playing. You toss the ball up to serve. Does the ball go flying to the back of the tram because you're moving?
No.
Mm-hmm.
Assuming the tram isn't turning or braking, the ball acts exactly like it would in my basement. It goes straight up and comes straight down.
Right. You can jump up and down, and you land in the same spot. If you pour a drink, it goes straight down into the glass. There is no experiment you can possibly do inside that tram to prove that you are moving.
I could be moving at 30 miles per hour, 300 miles per hour, or 0 miles per hour. It would all feel exactly the same.
Exactly. Now, let's open the blinds. You see a man standing by the side of the tracks. He is at rest relative to the ground. He watches you play ping pong.
Okay.
You hit the ball. You see it bounce on the table. 1 second later, you see it bounce again in the exact same spot on the table.
Right. From my perspective, the ball traveled 0 distance horizontally between those two bounces. Just up and down.
But what does the man on the track see?
Well, in that 1 second between bounces, the tram has moved. Let's say it's moved 40 feet.
So the man on the track sees the ball bounce, then travel 40 feet sideways through the air, and then bounce again. He sees a long zigzag path. You see a short, straight, up and down path.
Oh, true. So, who is right? Who describes the real path of the ball?
Newton's laws say, you are both right. There is no master coordinate system. There is no absolute point in space where the bounce happened. You define the position relative to the tram. He defines it relative to the track. Neither of you has a claim to absolute space.
And this drove Newton absolutely crazy.
It really did. Newton was a deeply religious man. He had this theological view that space was God's sensorium, the absolute unchanging stage where God observed the universe.
He wanted a fixed grid, a cosmic map.
He needed it for his theology to work. And the idea that position was relative, that you couldn't say, this is exactly where this event happened in an absolute sense, it conflicted with his idea of an absolute God.
So his own math was undermining his own beliefs.
He struggled with it his whole life. He tried to argue for the existence of absolute space, even when his own physics didn't require it. It was a huge point of criticism against him.
Bishop Berkeley had a bone to pick with him on this.
Oh, Berkeley went the full philosophical route. He was an idealist. He argued that if we can't define absolute position, then maybe space itself is just an illusion. Maybe matter is an illusion. He said all that exists is our perception of things.
And I had to bring up Dr. Johnson's response because it's my favorite moment of pettiness in philosophical history.
It's legendary. So Dr. Johnson is out walking with a friend, and they're talking about Berkeley's theory that matter doesn't really exist. And Johnson just walks up to a large stone by the roadside, kicks it as hard as he can, stubs his toe violently, and shouts, "I refute it thus!"
Which, to be fair, is a pretty compelling argument.
It is. The pain in your toe feels pretty real. But while they were all arguing about whether space was absolute or relative, there was one thing they all agreed on, one thing that was sacred and untouchable.
Time.
Absolute time. They all believed, Newton, Aristotle, the man on the tram, the man on the track, that a second is a second is a second.
Right, if I check my watch in the tram between those 2 ping pong bounces and the guy on the track checks his watch, we both measure the exact same duration. 1 second.
It seemed obvious, self-evident. Time was seen as a great cosmic river that flows at the same speed everywhere in the universe, completely separate from whatever space or matter is doing.
And that assumption, that common sense belief in absolute time, is exactly what was about to get completely destroyed. But the attack didn't start with clocks. It started with light.
Yes. The speed of light is the key that unlocks this whole mystery.
So pre-17th century, the general assumption was that light is instantaneous. You uncover a lantern and the light is everywhere at once. infinite speed.
Which is an understandable mistake. On Earth, over human distances, light moves so incredibly fast it appears instant. But in 1676, a Danish astronomer named Ole Christensen Romer realized something was wrong. And he wasn't looking at lanterns, he was looking at Jupiter.
More specifically, the moons of Jupiter.
Specifically Io, one of the big moons. It orbits Jupiter very, very regularly. It passes behind the planet and eclipses at very precise intervals. It's like a giant clock in the sky. Tick, tock. Every 42.5 hours, roughly.
A cosmic metronome.
That's a great way to put it. But Romer noticed the metronome was dragging or speeding up. When the Earth was on the far side of the Sun, moving away from Jupiter in its orbit, the eclipses of Io seemed to happen progressively late.
And when Earth was on the near side, moving closer to Jupiter.
They happened on schedule or even a bit early.
Now, obviously, the moon Io doesn't know where Earth is. It's not changing its speed based on what we're doing.
Of course not. The machine is steady. Romer realized the only variable was the distance between us and Jupiter. When we were farther away, the signal, the image of the eclipse, simply takes longer to get to us.
He discovered that light has a travel time, a finite speed.
It was a massive conceptual leap. He did a rough calculation and got a speed of about 140,000 miles per second. The modern value is closer to 186,000 miles per second, but the exact number doesn't matter as much as a core fact. The speed is finite. It is not infinite.
Okay, so light takes time to travel. That's a huge step. Now fast forward about 200 years to 1865. The American Civil War is ending, and in Britain, a physicist named James Clerk Maxwell is rewriting physics.
Maxwell, perhaps the most underrated genius in the history of science. He took everything known about electricity and magnetism and unified them into a single, beautiful set of 4 equations.
And these equations didn't just describe what was known, they predicted something new. They predicted waves.
Wave-like disturbances in the electromagnetic field. Maxwell calculated the speed of these theoretical ripples, and the number he got was, well, it was the speed of light.
So light is an electromagnetic wave.
That was the conclusion, a revolutionary one. But this created a huge, huge problem, a paradox that started to keep physicists up at night.
Why? What was the paradox?
Well, because of waves. Think about any wave you know. Sound waves are a vibration of air. If you take away the air, like in space, sound can't travel.
Right.
Ocean waves are a vibration of water. Take away the water, no waves.
You need a medium, something to do the
You
waving.
need a medium. So the scientists of the 19th century look at light waves and said, okay, what is waving?
But space is empty. We call it a vacuum for a reason.
They couldn't accept that. A wave and nothing made no sense to them, so they invented a substance, an invisible, undetectable substance. They called it the luminiferous ether.
This invisible goo that fills the entire universe.
They imagined the ether was everywhere, inside atoms, between planets, filling all of so-called empty space. And they thought light waves were just vibrations traveling through this ether.
And this brings us right back to Newton's problem of absolute rest. If the ether is everywhere, then the ether is the fixed stage that Newton was looking for.
Exactly. They thought, aha, we found it. The ether is the thing that is truly at rest. We are just moving through it.
And if we are moving through it, we should be able to measure that motion.
Think about being on a boat in a river with a current. If you row downstream with the current, you go faster. If you row upstream against the current, you go slower relative to the riverbank.
Or like walking in the wind, you feel it on your face.
Precisely. So they reasoned. The Earth is spinning on its axis at 1,000 miles an hour and orbiting the Sun at an incredible 67,000 miles an hour. We must be plowing through this stationary ether. We should feel an ether wind.
So the speed of light should change depending on which way we look. If we measure a beam of light traveling in the same direction as Earth's motion through the ether, it should seem to go a little bit faster.
And if we measure light going perpendicular to that motion, it should be different. That was the prediction. And in 1887, 2 American physicists, Albert Michelson and Edward Morley, set out to prove it.
They built this incredibly sensitive device, an interferometer.
It split a beam of light, sent the 2 halves on paths at right angles to each other, one with the supposed wind, one across it, and then brought them back together to see if one was delayed.
They were ready to measure the ether.
Yeah.
They were ready to finally confirm the fixed, absolute framework of the universe.
And they found nothing.
Zero difference.
Absolutely zero. No matter how they oriented the machine, no matter what time of day or year they ran the experiment, the speed of light was exactly the same in all directions.
I feel like we skip over this too fast in history books. This must have been absolutely terrifying for them.
It was a catastrophe. It was a crisis in physics. Imagine if you were in a convertible driving at 100-mile-an-hour and you threw a baseball forward, but an observer on the side of the road measured it going at the same speed as if you'd thrown it while standing still. It makes no logical sense.
It contradicts Newton and Galileo. Speeds are supposed to add up. My speed plus the ball's speed.
Exactly. So scientists went into panic mode. They started inventing these crazy ad hoc explanations. A physicist named Hendrik Lorentz suggested that maybe the ether wind physically squashed the measuring device.
That objects actually contract in the direction of motion.
Just enough to perfectly hide the effect. They were inventing epicycles. They were desperate to save the ether. But then in 1905, a 26-year-old clerk at the Swiss Patent Office in Bern decided to stop trying to save the old theory.
Albert Einstein.
Einstein looked at this complete mess and said, essentially, what if the experiment isn't wrong? What if it's right?
What if there is no ether?
He just threw it out. He stripped everything away. He proposed a fundamental postulate. The laws of physics are the same for all freely moving observers, no matter what speed they're traveling. And if that's true, it implies that the speed of light in a vacuum is a universal constant.
So if I'm sitting on my couch and I turn on a flashlight, the light travels away from me at 186,000 miles per second.
Yes.
And if I'm in a rocket ship, chasing that beam of light at 99.9% of the speed of light.
You would still measure that beam of light pulling away from you at 186,000 miles per second.
That feels impossible. My common sense, my brain is screaming that I should be catching up to it.
Common sense says speeds add and subtract. Einstein said, no. The speed of light is the one universal absolute. It is the cosmic speed limit. It does not change.
But something has to give. If speed is just distance divided by time, and the speed is fixed, but my motion, the distance, is changing.
Then time and distance themselves must change to keep the ratio constant.
And this is the mind bender. This is special relativity.
To keep the speed of light constant for everyone, Einstein showed that for a moving observer, space has to shrink in the direction of motion, and time has to slow down.
So if I'm on that rocket ship, my ruler actually gets shorter, and my clock ticks slower.
Relative to someone on Earth watching you, yes. It's not an illusion, it's a real physical effect.
And this leads us directly to the most famous equation in the world, EC22.
It falls right out of the mathematics of the theory. Mass and energy are just two different sides of the same coin, but it also gives us a physical reason for why you can't go faster than light.
Explain that mechanism. How does the equation prevent it?
Okay, so as you accelerate an object, you are pumping energy into it, kinetic energy. But Einstein showed that energy has mass. Energy is mass. So the faster you go, the more energy you have, and the heavier you effectively get.
So as I approach the speed of light, my mass is increasing.
Your inertia increases. It becomes harder and harder to accelerate you further. As you get to 99.999% of light speed, your effective mass is approaching infinity. You would need an infinite amount of energy to push you over that last tiny fraction of a percent.
Which the universe doesn't have.
Correct. So nothing with mass can ever reach the speed of light. Only massless things like photons, the particles of light, can travel that fast, and they must travel that fast. They have no choice.
But let's go back to time, because this is where the absolute time of Newton finally dies a very public death.
It's gone. In Einstein's world, there's no master clock for the universe. Every single observer, every object in the universe carries its own personal time.
The source material brings in a really helpful way to think about this using coordinates. The Piccadilly Circus analogy.
It's a great way to start to visualize space-time. So normally we think of space as having 3 dimensions. If we want to meet in London, I could tell you, go to a point 2 miles north and 3 miles west of Piccadilly Circus.
2 numbers, a north coordinate and a west coordinate.
But those directions are arbitrary, right?
Yeah.
We could just as easily look at the map and say, let's define our axes as northeast and northwest. We can rotate the map.
Sure, the physical point is the same, but the description, the coordinates would change.
Exactly. You are mixing northness and westness to create new coordinates. Einstein's great insight was that time is just a 4th dimension. And just like rotating a map mixes north and west, moving through space mixes your space and time coordinates.
So time isn't some separate thing flowing in the background. It's part of the same fabric as space.
Correct. It's a single 4-dimensional loaf of bread called space-time. Every observer slices that loaf at a slightly different angle depending on how fast they are moving. What you call space and what you call time depends on your slice.
That is deeply abstract.
Let's make it a bit more concrete with the idea of light cones. This is a concept that helps explain why there is no universal now.
The text uses the ripple in a pond analogy again here.
Right. Imagine dropping a stone in a pond. The ripples spread out in a circle. Now imagine stacking photos of those ripples, one on top of the other, second by second. The circles get bigger as you go up in the stack. It forms a cone shape.
Like an ice cream cone, expanding upwards through time.
That is your future light cone. The tip of the cone is you, right here, right now. The inside of that cone contains every event in the universe you can ever affect. Since you can't travel faster than light, you can't get a signal to anything outside that cone.
And there's a cone below me, too, pointing down. The past.
That's your past light cone. It's an inverted cone, and it contains all the events in the universe that could have sent a signal that reached you by now.
But there's a whole lot of universe outside those two cones.
And that region is called the elsewhere. This is the truly spooky part of relativity. Let's take the sun as an example. It's 93 million miles away. Light from the sun takes about 8 minutes to get here.
Right. I'm with you.
Okay. If the sun were to explode right now,
I wouldn't know for 8 minutes.
it's not just that you wouldn't know. The event physically has not reached you. For you, it hasn't happened yet. It is in your elsewhere. For the next 8 minutes, the sun is both exploded and not exploded, depending on where you are in the universe.
So saying the sun is exploding now is a meaningless statement.
Exactly. Now is a local illusion. There is no universal now that covers the whole universe at once. The explosion only becomes real to you when that event enters your past light cone 8 minutes from now.
That makes me feel incredibly isolated. We're all just trapped in our own little time bubbles.
We are connected to the rest of the universe only by the speed of light.
So Einstein fixes the ether problem. He unifies space and time. He wins the Nobel Prize. We're done, right? Physics is solved.
Not even close. He had solved the problem of light in constant motion, but he had created a brand new problem with gravity.
Why? What's wrong with gravity? It worked pretty well for Newton.
Special relativity says nothing travels faster than light. No signal, no information, no object, nothing.
Okay, that's the new rule.
But Newton's theory of gravity, the one that works so perfectly for the planets, said that gravity is instantaneous. Newton thought that if the sun suddenly disappeared, the Earth would instantly stop feeling its pull and fly out of orbit.
Faster than the speed of light.
Infinitely fast. So Einstein has a major conflict. His new theory of special relativity, which he knows is right, directly contradicts Newton's theory of gravity. He knew Newton had to be wrong about gravity.
That takes some serious confidence. Newton is wrong.
It does. But Einstein spent nearly a decade, from 1908 to 1915, trying to solve this. It was, by his own account, the most brutal intellectual struggle of his life. And the answer he found is general relativity.
And this brings us to the airplane shadow analogy from the source material, because this is the part where we learn that gravity isn't a force at all.
This is the hardest conceptual leap in all of physics, I think. We feel gravity as a pull, it feels like a force. But Einstein said, there is no pull.
My feet are stuck to the floor.
Yeah.
That feels very much like a pull.
It's an illusion caused by geometry. Einstein's great idea was that mass and energy like the Earth or the sun warp the very fabric of space-time itself.
So it curves the grid.
Think of the airplane analogy. Imagine a plane flying the Great Circle route from New York to London. In the air, in 3 dimensions, it flies in the straightest possible line, the shortest path.
A straight line. Okay.
And now look at its shadow on the ground below. The ground isn't flat. It has hills and valleys. As the plane flies straight, its shadow has to move up and down over the hills. To a 2D creature living on the ground, the shadow's path looks curved.
Right. It's following the bumps in the terrain.
Einstein said, "We are the shadow. The Earth is trying to move in a perfectly straight line through 4-dimensional space-time. This straightest possible path is called a geodesic.
But because the sun, which is massive, has curved the space-time around it.
That straight path gets bent into a circle. The Earth isn't being pulled by some invisible rope. It's just rolling along the natural curve of the universe like a marble in a bowl."
That is wild. So it's like a marble rolling around in a big salad bowl. It thinks it's going straight, but the shape of the bowl forces it to go in a circle.
That's a perfect analogy. Gravity is just the shape of space-time.
This sounds beautiful and poetic,
Okay.
but again, science needs proof. You can't just say space is curved and expect people to believe you, right?
And Einstein knew that. His theory made 3 very specific, testable predictions. The first was about the planet Mercury.
The planet closest to the sun, where gravity is strongest.
Mercury's orbit is a little weird. It doesn't trace the same ellipse over and over. The whole ellipse itself rotates slowly over time. It precesses. Newton's laws predicted most of this precession, but not all of it. There was a tiny nagging error that no astronomer could explain.
And Einstein.
He plugged the numbers into his brand new equations of general relativity, and they predicted the wobble of Mercury's orbit perfectly, to the exact decimal place.
Okay, that's one. But that's explaining something we already knew was happening. What about predicting something totally new?
That was the big one, bending light.
If gravity curves space, then a beam of light passing through that curved space should curve too.
Exactly. Light always follows the geodesic, the straightest path. So Einstein predicted that if light from a distant star passes close to the sun, its path should be bent by the sun's gravity. This means the star would appear to be in a slightly different position in the sky.
But you can't see stars when they're right next to the sun. The sun is a little too bright.
Unless you turn off the sun.
At a total solar eclipse.
The 1919 eclipse. A British astronomer, Sir Arthur Eddington, led an expedition to an island off the coast of West Africa. They waited for the moment the moon completely blocked the sun, and they took photographs of the Hyades star cluster, which was right next to the darkened sun at the time.
And the result.
They compared those photos to photos of the same star cluster taken 6 months later at night. And the stars had shifted, the light had bent. The newspaper headlines the next day were insane. Lights all askew in the heavens, revolution in science, Newtonian theory overthrown. Einstein became a global celebrity overnight.
Now, I have to bring up the luck factor mentioned in the source, because apparently science isn't always as clean and perfect as the headlines make it seem.
It's true. Later, more sober analysis of Eddington's 1919 photographic plates showed that the measurements were actually really messy. The margin for error was huge. Technically, the data was pretty inconclusive.
So they kind of saw what they wanted to see.
There's definitely some confirmation bias going on. Eddington knew what the answer should be, and his data was just good enough to claim victory. It was sheer luck that he happened to be right. But, and this is a very important, but countless later experiments with much better technology have confirmed it to an incredible degree of precision. Einstein was right, even if Eddington's initial proof was a bit optimistic.
Okay, so we have wobbly Mercury, we have bent starlight. But the third prediction is the one that brings us back to my clock on the water tower.
Gravitational time dilation.
This is the idea that gravity actually slows down time.
Yes. Think about light again. Light is a wave, and it has energy. When a beam of light climbs out of a strong gravitational field like leaving the surface of the Earth, it has to fight against gravity. It loses energy.
And for light, losing energy means what? It doesn't slow down.
It can't slow down, so its color changes, the frequency drops, it gets redshifted, the waves get stretched out. A lower frequency means the ticks of the light wave happen slower.
So to someone watching from high up, the light coming from down below looks like it's vibrating in slow motion.
And since everything is ultimately made of atoms and energy that behave like waves, everything down below looks like it's happening in slow motion. Time itself runs slower where gravity is stronger.
So my feet are aging just a tiny bit slower than my head.
By a tiny, tiny infinitesimal fraction, yes.
And the water tower experiment. They actually tested this.
In 1962, scientists finally had atomic clocks accurate enough to test this on Earth. They put one ultra-precise clock at the bottom of a water tower and another one at the top.
And the bottom clock ran slower.
It did, exactly as Einstein's theory predicted.
I have to ask the skeptic's question here. Does this actually matter? Are we talking about billionths of a nanosecond that only physicists with atomic clocks care about?
We are talking about billionths of a second, yes. But if we ignored it, your life would literally break.
How so?
GPS.
The map on my phone.
Your phone calculates its position by listening to signals from at least 4 different satellites. Those satellites are orbiting 12,000 miles up, where gravity is significantly weaker.
So their clocks run faster than ours on the ground.
They run faster by about 45 microseconds every single day compared to clocks on the ground. That's a combination of this gravitational effect and the special relativity effect from their high speed.
45 microseconds. That still sounds negligible.
In terms of how fast light travels, 45 microseconds is a huge amount of time. Light travels about 300 meters in just 1 microsecond. If the GPS engineers didn't program Einstein's equations of both special and general relativity into the satellites to constantly correct for this time drift,
What happened?
the system would be off by several miles within a single day. Your GPS would tell you your favorite coffee shop is in the middle of a lake.
So if I drive to a coffee shop using Google Maps, and I actually arrive there, I have general relativity to thank for my latte.
You are literally navigating through the real world by using the curvature of space-time.
That is mind-blowing.
Yeah.
Okay, we have to talk about the twin paradox before we wrap up. Because this is the sci-fi staple. Everyone knows this one.
It is. The paradox goes like this. You have two identical twins. One stays on Earth. The other one gets in a super fast spaceship and flies to a nearby star at, say, 90% of the speed of light, turns around, and comes back.
And when he steps out of the ship?
He is noticeably younger than his twin who stayed home. Maybe he's aged 10 years while his twin on Earth is aged 30.
So why is it a paradox?
Because of the principle of relativity. From the spaceship twin's perspective, he was the one who was still, and the Earth zoomed away from him and then came back. So shouldn't the Earth twin be the younger one? If all motion is relative, why is the effect one-sided?
That's a good question. Why is it one-sided? Who's right?
The Earth twin is right. The situation isn't symmetrical at all. The Earth twin just sat on the couch coasting through space-time. But the space twin had to fire his rockets. He had to accelerate to leave, stop at his destination, turn around, which is a huge acceleration, and accelerate back.
He felt the G-forces. The Earth twin didn't.
Exactly. By changing his speed and direction, the space twin shifted through different frames of reference, different slices of space-time. His path through the 4D universe was physically shorter in the time dimension than the path the Earth twin took.
So he literally took a shortcut through time by taking the long way through space.
In a way, yes. It's not a paradox if you abandon the idea of absolute time. It's just geometry. The longest time between two events in space-time is the straight line, the path of the person who doesn't accelerate. The traveler took a curved path, and that path covers less time.
I think my brain is fully melted now, which I think means we're doing it right.
That means we're making progress.
So let's zoom out for the finale. We started with Aristotle and Newton, and for them, the universe was a stage. It was a fixed, eternal, unchanging box that things happened inside of.
A static container, yes.
And where have we ended up after this journey?
We've ended up with a dynamic living entity. Space and time are not the container. They are the actors on the stage. They warp, they bend, they stretch, they ripple. Matter tells space how to curve. Space tells matter how to move.
And this leads to the biggest, most profound implication of all. If space-time is dynamic,
then the universe itself can change. It can expand or contract.
and if it's expanding, as we now know it is, that means in the past it must have been smaller.
And if you go back far enough in time, everything was crushed into a single point of infinite density.
The Big Bang.
And this brings us to the final provocative thought from the source material, something that was at the heart of the work of physicists like Roger Penrose and Stephen Hawking.
The beginning of time itself.
If space and time are intrinsically linked, if they are generated by the matter and energy of the universe, then you cannot have time without the universe existing.
So asking the question, what happened before the Big Bang, is...
It's a meaningless question. Hawking famously compared it to asking, what is north of the North Pole?
There's nothing north of the North Pole. You're just... you're at the pole. The concept of north ceases to exist there.
Exactly. Time began at the Big Bang. There is no before. The universe didn't appear in time. Time appeared with the universe.
That is a thought that will keep me awake tonight.
It should. It's the ultimate boundary of our understanding.
So when our listeners look up at the night sky tonight,
Don't just see a bunch of dots of light. Realize you are looking deep into the past. You are seeing ghosts of stars as they were years or millions of years ago. And realize that the darkness between those stars isn't empty. It's a fabric. It's a heavy, curved, dynamic fabric that is guiding the planets, slowing down your clock, and holding your entire reality together.
and maybe remember, because your feet are on the ground, you are aging just a tiny, tiny bit slower than the astronauts on the International Space Station. So enjoy those extra nanoseconds.
Use them wisely.
Thanks for diving deep with us. We'll see you next time.